oilers flammable gas with the chemical formula of CH4. To our environment, it can cause greenhouse effect. Hence, to make the good use out of it, it is used in the steam reforming process in methanol production, which convert and utilize the methane to methanol. This methanol is applicable in production of acetic acid and formaldehyde. Our integrated project is about proposing design solutions on methanol production through steam reforming process. Hence, the design solution and discussion of this project will be revolving around separation process 1 and thermodynamics 2.
For design task A, we need the equation of the vapor-liquid equilibrium inside the flash distillation of the methanol purification unit, which is labeled as D103. So, in this task, we'll have 3 parts, which is part 1, part 2, part 3. So, for part 1, it's about to predict the vapor composition of both methanol and also for water. So, the first step is we have to use the Anton equation to find the value of P set for water and also for methanol. So next, after we solve the Anton equation, we have to key in the value of liquid composition for methanol, and then we'll have the liquid composition for water. Then after that, we use this formula, P equals to x1, P1 set plus x2, P2 set to get the value of P from both of these values. After we get the value of P, we'll insert this formula, and then we'll get the vapor composition for methanol. To get for the water, we use the same formula, but insert the different value, which is the value for water instead. For the next part, we have to predict the liquid composition Xi for both water and also for methanol. So, for the first step, we have to use the Anton equation to find the P set for methanol and also for water. Then we have to assume the value of vapor composition of methanol to get the vapor composition of water. Then we have to use this formula to find the P, which is 1 over Y over P1 set plus Y over P2 set. And then after we get the P, we can find the new liquid composition of water and also for methanol by using the same formula. So for task 3, we have to predict the vapor composition YI and also the liquid composition Xi for the methanol and also for the water. So first step is to find the P set is an Anton equation. Next is we have to key in the overall position for methanol to find the overall composition of water. Next is by assuming the overall composition of water and methanol is equal to the vapor composition and liquid composition of water and methanol, we can use the formula of P bubble and also P dew to find the limitation of the flash distillation. So next we will find the K using the Y over X. So after we find the K, we can key into this formula and do some iteration to find the value of V. After we find the value of V, we can find the value of L because L is equals to 1 minus V, and then we can find the value of X and Y using the Raoult's law that we have explained in task 1 and task 2. That's all. I would like to show you about our macro program. So for the first task, we have to find the vapor composition of methanol. So we click this button, and the cell will ask for the liquid composition of methanol. When we key in a value of the composition, press enter, the vapor composition of methanol will appear. So next, for task 2, we have to find the liquid composition of methanol. So when we press this button, it will ask us the vapor composition of methanol. So we key in a value, then the vapor composition of methanol will appear. For the third task, it asks us to find the vapor over liquid mole fraction, vapor and liquid composition of methanol and water. When we click the button, it will ask the overall composition of methanol. Press enter, then it will ask us about the pressure that we want to key in inside the system. Then the value of K, X and Y will be shown. Okay, so for my problem is from question 3.19. So in this question, it asks us to, the first question is asked us to draw the PV diagram for the whole process. So for the PV diagram, for point 1, we can use the equation of ideal gas P1 equals to T1. For the point 2, we know this is the isothermal process, so we can use T1 equals to T2. Then we can use the relation P1 equals to P2 V2. So for V3, we'll have V2 equals to V3, so it's an isochoric process. From point 4, we have to use the adiabatic relation from 4 to 1. So this is an adiabatic process. And I discussed the problem 6.85. They estimate the Z, the residual enthalpy and residual entropy from the benzene and cyclohexane at 650 Kelvin and 60 bar. Firstly, we get the eccentric factor, the TPC1, eccentric factor 2, TPC2 and TPC from table B1. We can know from the problem, we can know the equimolar mixture y equal to 1. Then we can get the eccentric factor, TPC and PPC. Then we can get the TPR from this equation T over TPC and PPR from this equation P over PC.
So hi, I'll be talking about the problem 30.1 in chapter 15. So assuming the validity of Raoult's law, do the following calculation for the benzene and toluene system. So get this data from the table in the appendix, and then from this data using an equation for this problem, which is given as y equals to 0.33 and temperature equals 1 degree Celsius, find y1 and p. So try to find P1 saturated and P2 saturated. So from that, use that to insert the Raoult's law, which is S1 P1 set plus S2 P2 set to get the P, and then obtain the P of Y1 by Y1 P is to S1 P1 set. Moving on to P, which is given Y1 equals 0.33 and temperature 100 degrees Celsius. Find S1 and P. So using your edited equation, get the P1 saturated and P2 saturated again. And then using Raoult's law, Y1 equals S1 P1 set plus S2 P2 set equals S1 P1 set to obtain your S1. And to obtain your P is by obtaining S1 P1 set plus S2 P2 set.
Now I discuss the problem of task B. The task B need to decide the methanol purification unit and calculate the number of theoretical stages. From the problem, we know the small f, and we assume the feed. Then we can calculate the distillate column, distillate. Then from this material balance, we can get the B and SD and SB. After that, we can plot a graph with equilibrium data and plot the point of SD, SF and SB. Then we take the feed condition represented by the quantity of Q. The Q equal to latent heat of vaporization plus average heat capacity multiply the boiling point of temperature minus the feed of temperature that given is 66 degrees Celsius. Then over the latent heat of vaporization. After we get the Q, we can see from the graph. Then Q bigger than 1, there's compressed liquid. Q equal to 1 is saturated liquid. Q between the 0 and 1 is saturated mixture. Q equal to 0 is saturated vapor. And Q less than 0 is superheated vapor. After we can get the Q value, we can find the Q line with this equation. Y equal to Q over Q minus 1 multiply X minus feed over Q minus 1. Then we can plot the rectifying line with this formula. Y equal to R over R plus 1 X plus SD over R plus 1. Then we can plot the Q line and the rectifying line. From the intersect point, we can draw the stripping line until the X bottom. The question need to determine the ultimate refraction and calculate the number of theoretical stages. So from this graph, we can draw another line to the finish point that is touch the Q line and the equilibrium line. Then this finish point is used to calculate the minimum refraction ratio. They use this formula. After calculate the Rm, we can take the range from 1.2 to 1.5 to calculate the new R. After calculate the new R, we can get a new rectifying line and new stripping line. Then we can calculate the theoretical stages. For our problem, the SF is near the SD. After calculate our minimum refraction ratio, the intercept point with R and Q line is out of the equilibrium curve, so we cannot calculate the number of theoretical stages.
divided into task A and task B. In task A, we were required to estimate the BLE condition by assuming ideal gas and ideal solution. By using Einstein's equation and Raoult's law, we were able to solve the problems as these methods were learned in thermodynamics too. While in task B, we were required to estimate the number of theoretical trays by designing the distillation column at optimum default ratio. The distillation column was designed using mathematical method as taught in separation process 1. In conclusion, we believe that the objectives of integrated design project are achieved as we managed to utilize the courses which we have learned throughout this semester in this project.